how much computational effort is needed to solve the problem. But anyway, that's part 3, sort of you're a month or more away. Okay, so this new kind of automaton is called push down, and because what you're doing, you're taking a symbol and you're pushing it onto the stack. So if you imagine a stack of plates and a loaded spring underneath the pile of plates, or the stack of plates, then as you put another plate on top of the stack, that's the extra weight of that stack of plates or pile of plates will press on the spring a bit more because there's greater weight on it, and so the spring will compress a bit more and the stack of plates will move down a little bit. Okay, so in a sense you're pushing down on the spring, or on the stack, so to speak. So hence push down automata. Okay, so it's a new kind of computational model. It's somewhat like an NFA, but like I was saying, the stack that the push down automaton has can be infinitely deep, right? So therefore the F here is no longer appropriate for a push down automaton. It is not finite, right? It has the capacity to memorize infinite amount of information. You can put an infinite amount of information on the stack, right? You're just by piling more and more things, usually just symbols, on the stack, right? One on top of the other. So the earlier things that you put on the stack get buried, so to speak, and you can't read them, you can't get at them until the things that are above it on the stack are removed. Right? But I'm getting a bit ahead of myself. Okay, so the essential concept of the stack. Now, by using a stack, in other words, using the push-down automaton, you can actually recognize some non-regular languages, and that means they have a greater power than DFAs. So many abbreviations now, so many acronyms. I'm forgetting. So a deterministic finite automaton, right? So by definition, a language is regular if it's recognized by a DFA. Okay. So a stack-based automaton, in other words, a push-down automaton, is more powerful than a DFA. Why? Well, because it can recognize some non-regular languages. That by definition, if a language is non-regular, it means there is no DFA that can recognize it. Therefore, push-down automata are more powerful than DFAs because they can recognize a wider class range set of languages. Right? So that's what this is saying here. Okay, now I've put here in three bars, if I do, or 2 or 3 bar vertical bars, if I do something like that, that's a statement that's really important. What is that statement? It says, well, these PDAs, these push-down automata, now that's an abbreviation I'll use a lot from now on, PDAs. So push-down automata, they're equivalent in their power, so they can recognize the same set of languages, to CFGs, to context-free grammars. Okay? So in other words, now you can remember the previous chapter, chapter 1, we had an equivalence between DFAs and regular expressions. Sorry? Was it NFAs? Forgetting. Anyway, there was an equivalence between regular expression and an automaton, a machine. Now here you've got something similar. Okay? So you have an equivalence between the push-down automaton, PDA, and a grammar. Okay? So there'll be theorem. You can expect theorems about this. Now, if they're equivalents, you can almost, given Sipser's style, there's going to be a theorem of the form if and only if, right? If it's a push-down automaton, therefore there'll be a CFG. And the other half of the if and only if theorem that you can anticipate coming will be if it's a CFG, then there's an automaton, right? So there will be those two parts, and you'll probably put them in lemmas, two lemmas. Okay, so expect that coming, right? Now, okay, so yeah, very important here that again we've got an equivalence between a machine and something else. In this case, the something else is a grammar. Before the previous chapter, it was a regular expression. Okay. Now, this equivalence, this one here, it's useful. Why? Because now, if there's an equivalence between a grammar, CFG, and the machine, the automaton, in this case a push-down automaton, PDA, then that means you now have a second way to describe a language, right? One way is well, context-free language, CFL, all these abbreviations. You got a lot to memorize. Okay, a lot of acronyms in this subject, in this topic. So now before, not to this chapter at least, we defined a CFL, a context-free language, as a language that was described by a grammar, a context-free grammar. Okay. Well, now we've got a second way to describe the language because of the equivalence of the language and the machine, the push-down automaton, PDA. So, so now this second way of describing the language is that there is a machine, a PDA, push-down automaton, that what's the verb? Recognizes it? I guess. Yeah, recognizes it. Okay, so we now have a second way, a second tool, a second approach to showing that a language is context-free. Okay, so important. We've got a whole new doorway opens up. We have a second option. All right. Now, this comes out of experience, this statement here. It says that some languages you can describe more easily with using generators, in other words, grammar. That's what the grammars do. They generate strings, hence the language. Right? So some languages you can describe more easily using grammars, okay, CFGs, and other languages you can describe them more easily by using recognizers, in other words, a machine, a PDA. Okay? And that just comes out of experience, but it's useful to know. Right now, so have a look at this little diagram here. Now this is our typical automaton, right? So you have some kind of state control, typically the control of states. So you'll have a list of states, and you'll have transition rules, and you'll have the current symbol that's being read, and the current one's pointed to by this arrow, let's say. So here's your input stream coming in, and the arrow points to the symbol that's currently being read. In this case, I think the convention is it's the next input symbol to be read. Okay, so it's pointing to the next one to be read. And the state control will consist of the set of states, in other words, big V, and no, hold on, we're talking about a machine. Careful, we're talking about a machine. So we're talking about a set of states, and we're also talking about the transition rules. From the current state with the current symbol being read, giving the next state. Okay, so the transition function, the delta, and the set of states, that's this block here. Right? Call that state control, generic term. And this arrow points to the next input symbol to be read in your input stream coming in. Right? Now, you can't see it, but it's in the next session. We will draw this diagram again, and we'll add a second arrow pointing down to the stack. Okay? And that arrow points to the symbol that is currently on the top of the stack. Okay, and so with the stack we can read what's on the top of the stack and then pop it. Now I've talked a bit about pushing and popping before, but I'll go into it again next session. But you can read the top element on the stack and pop it, read it and then throw it away. Or you can put an element and push it. You put it onto the top of the stack, and that arrow, that second arrow, now points to that new top element, and all the other elements in the stack get pushed down one. Okay, just like a stack of plates with a spring underneath. Okay, so I'll stop there.